Before the Earth existed, before the Sun existed, before even the solar system existed, there was a star. Not our star, a different one. A massive, ancient star that had been burning for millions of years, somewhere in the arm of what we now call the Milky Way galaxy. This star was enormous, many times larger than our Sun, and it had spent its entire life doing one single job, fusing lighter elements into heavier ones deep inside its core, powered by the unimaginable pressure of its own gravity pressing inward from all directions. For millions of years it did this quietly, reliably, and invisibly in the darkness of space. Then it died. And that death, that single violent moment of cosmic destruction, is the reason you are sitting here watching this video right now. To understand why that matters, we have to go back even further, back to the very beginning of everything. When the universe was born roughly 13.8 billion years ago in what scientists call the Big Bang, the only elements that came out of that first explosion were the simplest ones: hydrogen, helium, and tiny traces of lithium. That is it. The entire universe started with just those three ingredients. No carbon, no oxygen, no iron, no calcium, no silicon, no gold, nothing complex. Just the lightest, most basic building blocks imaginable, floating in an expanding cloud across an early universe that had no planets, no rocks, no chemistry complicated enough to produce anything like life. If the universe had stayed that way, nothing interesting would ever have happened. Earth could never have formed. Life could never have emerged. The universe would have remained forever simple, cold, and empty of meaning. But gravity had other plans. Across hundreds of millions of years, those clouds of hydrogen and helium slowly pulled together under their own weight, gathering and compressing until the pressure at the center of each growing clump became so intense that atoms were forced to merge. This is nuclear fusion. When hydrogen atoms are squeezed together hard enough, they combine to form helium, and in doing so, they release an enormous burst of energy. That released energy is what makes a star shine. Our ancient pre-solar star ignited this way, a furnace switching on in the darkness, pouring light and heat into the surrounding space. What happened inside that star over the millions of years it lived is the part that should genuinely stop you in your tracks. As the star burned through its hydrogen, it began fusing helium into carbon, then carbon into oxygen, then oxygen into neon, neon into magnesium, magnesium into silicon, and silicon into iron. Each step required more pressure, more heat, and each step produced heavier and more complex elements. The star was, in the truest sense of the word, a factory. It was manufacturing the raw materials of the physical world, one atomic layer at a time, building up like the layers of an onion deep inside itself. Carbon, the backbone of all life on Earth, was forged inside a star. Oxygen, the gas you are breathing right now, was forged inside a star. Every element heavier than helium that exists naturally in your body, in the soil, in the oceans, in every mountain and every drop of rain, was produced inside the nuclear furnace of a dying star. Then the star reached iron. Iron is where everything changes. Every element up to iron releases energy when it is fused. But iron is different. Iron absorbs energy instead of releasing it. The moment a massive star's core fills up with iron, fusion stops producing the outward pressure that has been holding the star up against the crushing weight of its own gravity. In a fraction of a second, literally less than a second, the core collapses. The outer layers of the star, which have been held up by the pressure from below, suddenly have nothing supporting them. They fall inward at a significant fraction of the speed of light, crash into the now rigid iron core, and bounce back outward in the most violent explosion the universe is capable of producing: a supernova. The energy released in a supernova is almost impossible to hold in your mind as a real number. In those few seconds of explosion, a single dying star releases more energy than our sun will produce across its entire 10 billion year lifetime. The explosion is so bright that a supernova can outshine an entire galaxy of hundreds of billions of stars. The shockwave tears the star apart completely, hurling its entire outer shell. All those carefully forged elements, all that carbon and oxygen and silicon and iron, out into the surrounding space at thousands of kilometers per second. And in the extreme heat and pressure of the explosion itself, elements heavier than iron are formed for the first time: gold, silver, uranium, platinum. These elements cannot be made by ordinary stellar fusion. They require the violence of a dying star to exist at all. Every piece of gold on Earth, every gram of it, was forged in a stellar explosion before our solar system was born. That explosion from our ancient pre-solar star sent a shockwave rippling through the surrounding region of the galaxy. And that shockwave is thought to be exactly what triggered the next chapter of our story. About 4.6 billion years ago, a large cloud of gas and dust, enriched with all the elements that dead star had scattered, was drifting through space. The shockwave from a nearby supernova compressed that cloud. Gravity took over. The cloud began to collapse inward on itself, spinning as it fell. As it spun faster and faster, like a figure skater pulling their arms inward, it flattened into a rotating disk. At the center, material piled up and the pressure grew until nuclear fusion ignited again. Our sun was born. Around the newborn sun, the remaining disk of gas and dust did not simply float away, it began to clump. Tiny grains of dust collided and stuck together, forming pebbles. Pebbles collided and built boulders. Boulders accumulated into what scientists call planetesimals, objects kilometers across, tumbling through the early solar system, crashing into each other constantly in a process that went on for millions of years. These collisions were not gentle. They were catastrophic impacts that melted rock and vaporized material, only for gravity to pull it back together again. Slowly, gradually, the objects grew larger, and the larger they grew, the stronger their gravity, and the more efficiently they swept up the material around them. One of those growing bodies was in the region we now call the inner solar system, roughly 150 million kilometers from the sun. It was made of the exact same material that the ancient dead star had scattered across the galaxy: silicon, iron, magnesium, oxygen, carbon, and dozens of other elements, all mixed together and melting under the heat of constant bombardment. This was Proto-Earth. It was not yet the planet we know. It was a hot, molten, chaotic ball of rock and metal, constantly being struck by other objects, growing larger with each collision. Then came the single biggest collision in Earth's history, roughly 4.5 billion years ago. A planet-sized object, scientists call it Theia, smashed into the young Earth at an angle. The impact was so enormous that it partially melted both bodies, threw enormous amounts of material into orbit around the Earth, and that orbiting debris gradually gathered itself together under gravity into the Moon. The Moon, which controls our tides and has stabilized Earth's axial tilt for billions of years, creating the relatively stable climate conditions that made complex life possible, was born from that single catastrophic smash. After that, Earth slowly cooled. A solid crust formed over the molten interior. Water arrived, carried by icy comets and asteroids from the outer solar system, or released from volcanic activity from within the planet itself. Oceans formed. An atmosphere built up from volcanic gases. And in those early oceans, somewhere between 3.5 and 4 billion years ago, the chemistry of life began. Simple molecules made of carbon atoms forged in a dead star began arranging themselves into structures capable of copying themselves. And from that beginning, across billions of years of slow and patient change, eventually came everything alive on this planet today. What this means when you sit with it quietly is something almost too large for language. You are not separate from the universe. You are made of it. The iron in your blood was forged in a stellar core. The calcium in your bones was scattered by a supernova. The oxygen filling your lungs right now was built atom by atom inside a star that died before our sun was even born. You are, in the most literal and physical sense possible, stardust. The universe did not create life as an afterthought. It built the ingredients across billions of years in the hearts of dying stars and scattered them across the galaxy until gravity pulled them together into something that could breathe and think and wonder where it came from.